Hello everyone, I am Anika Tabassum Hossain. Today I am going to present our project on the advanced power converter design for the EV battery charging systems with my group mates Hasib Kamran and Yashodini Randonu. We have put together our work under the supervision of Ashraf Ali Khan sir and with the help of our project coordinator Mohsin Jamil sir. Let's have a quick look at the contents. Objective: Introduction, literature review, advantages of LLC converter in EV battery charging, working principle, design specifications, half bridge LLC converter with battery charging Simulink model, simulation results, and finally conclusion. Objective: Selection of an appropriate converter. To design our whole model, we selected resonant converter or LLC converter. Battery selection. We need a reliable, inexpensive, and lightweight battery to be used in the electric vehicle. Design and simulation using MATLAB. Introduction. It is no secret that gasoline powered vehicles are polluting the environment, and with the increase in fuel prices, electric vehicles have become very popular. But this widespread adoption of EVs has made it very important to design efficient components of EVs. Electric vehicle battery charging systems utilize LLC converters, which are power electrical devices. They efficiently transform the AC grid electricity into the necessary amounts of DC voltage for charging EV batteries. Resonant tank circuits are used by LLC converters to provide high frequency switching, lower losses, and increased efficiency. Our work examines the function of LLC converters in EV battery charging systems, highlighting their advantages, modeling and simulations, modifications, and potential for the future. Understanding LLC converters' complexities will help us better comprehend the technological developments influencing the EV charging environment, fostering the wider use of electric cars and a healthier, greener future. Literature review. According to Young Wei, an output parallel and output series hybrid topology of a half-bridge LLC resonant converter and phase-shifted full-bridge converter can achieve a high step-up conversion ratio. One of the advantages is that fixed switching frequency operation resolves the issues associated with a considerable switching frequency variation. LLC converters are not typically designed to handle such a broad voltage range, input voltage between 240 and 420 volt and output voltage between 8 and 16 volt. This LLC converter operates in a full bridge mode for high gains and half bridge mode for low gains. The LLC uses the phase shift mode for intermediate gains and loads. A 3.6 kilowatt prototype using silicon superjunction MOSFETs achieves 2.1 kilowatt power density. The highest efficiency is 96.5%, with most operating points above 90%. Duty cycle control is a typical method for restricting current in LLC resonant converters. The current limiting type is essential to safeguard the converter during startup or an overload. Standard duty cycle or phase shift modulation approaches do not naturally give this. Traditional frequency modulated LSC converters require an extensive frequency variation range and are difficult to scale. In disparity, conventional phase shifted LLC converters have concerns with soft switching loss and high turnoff current. In comparison to typical PS LLC converters, the suggested approach achieves the following: a more minor phase shift variation range, a lower turnoff current, a more extensive soft switching range, all of which result in improved efficiency. An 825 watt prototype with a 200 volt input and a 125 to 210 volt output range validated the suggested idea's characteristics, and the efficiency achieves 97.82% at maximum output power. The EV onboard charger is divided into AC-DC converters and DC-DC converters. The bidirectional DC-DC LLC resonant converter has been studied to increase charger efficiency in V2X mode across both battery power and voltage ranges in M.A. Hamida and her team's research. Based on the findings of various studies, it appears that half-bridge LLC type converters rather than other resonant converters are suited better for charging electric vehicles. Now, advantages of LLC converter in EV battery charging. LLC converters provide lots of benefits including strong load management, a wide input voltage range, gentle switching, low electromagnetic interference, high efficiency, and power factor correction. They function with high levels of efficiency, reducing power losses throughout the charging process. They become more energy efficient because of shorter charging periods and less energy use. Moreover, LLC converters use power factor correction methods. PFC guarantees that the grid's sinusoidal current is drawn by the charging system, enhancing power quality, lowering harmonic distortion, and adhering to rules and standards like IEC 6100032 by attaining a high power factor. A broad range of input voltages may be accommodated by LLC converter designs, allowing for versatility and compatibility with various EV charging infrastructures. The soft switching feature minimizes switching losses by switching the transistors at circumstances of nearly zero voltage or current. This increases power device longevity, reduces electromagnetic interference, and improves overall efficiency. LLC converters are suited for EV charging scenarios where stringent EMI requirements must be satisfied because of the decreased EMI emissions. The lightweight and small size of LLC converters make them ideal for EV charging facilities. Thin and light power electronic components are possible because of the resonant behavior of LLC converters. They offer superior load regulation, keeping a constant output voltage despite changing load circumstances, since the EV charging current can shift dramatically depending on the battery's level of charge and other variables. The battery is safeguarded from excessive charging or undercharging thanks to the output voltage's ability to be controlled.
My name is Yashodhini and I'm going to talk about the working principle of half-bridge LLC converter. A typical topology of an LLC half-bridge resonant converter is showed in the picture in the screen. So power switches Q1 and Q2, which are usually MOSFETs, are configured to form a square wave generator. This generator produces a unipolar square wave voltage by driving switches Q1 and Q2, which alternate in 50% duty cycles for each switch. A small dead time is needed between the consecutive transitions to prevent the possibility to cross conduction and to allow time for switching to be achieved. The resonant circuit, also called a resonant network, consists of the resonant capacitor CR and two inductances. And the series resonant inductance is called LR, and the transformer's magnetizing inductance called LM. The transformer turns ratio is N. The resonant network circulates the electric current, and as a result, the energy is circulated and delivered to the load through the transformer. The transformer's primary winding receives a bipolar square wave voltage. This voltage is transferred to the secondary side, with the transformer providing both electrical isolation and the turns ratio to deliver the required voltage level to the output. On On the converter's secondary side, the two diodes constitute a full wave rectifier to convert AC input to DC output and supply the load RL. The output capacitor smooths the rectified voltage and current. The rectified fire network can be implemented as a full wave bridge or center tapped configuration with a capacitive output filter. The rectifiers can also be implemented with MOSFETs, forming synchronous rectification to reduce conduction losses, especially beneficial in low voltage and high current applications. Fundamentally, the resonant network of an series resonant converter presents a minimum impedance to the sinusoidal current at the resonant frequency, regardless of the frequency of the square wave voltage applied in the input. This is sometimes called the resonant circuit's selective property. Away from resonance, the circuit presents higher impedance levels. The amount of current or associated energy to be circulated and delivered to the load is then mainly dependent upon the value of the resonant circuit's impedance at that frequency for a given load impedance. As the frequency of the square wave generator is varied, the resonant circuit's impedance varies to control that portion of energy delivered to the load. This table shows the design parameters of our MATLAB Simulink model. LSC operation can be categorized into three modes based on switching frequency. If the switching frequency is equal to the resonant frequency, it's called resonance mode. If the switching frequency is greater than the resonant frequency, it's called buck mode. And if the switching frequency is lower than the resonant frequency, it's called boost mode. Now I'm going to talk about the most important part, the battery selection for our Simulink model. We need a reliable, inexpensive and high, very lightweight battery to be used to our bike. So we selected a battery which was available on Amazon Canada. We selected this specific battery because it's inexpensive, easily available throughout the Canada and has excellent reviews. So you can see the battery specifications from Amazon in the slide right now. So because of the unique features and specifications which match the demands of an electric bike's power and performance, this battery is a good fit for our purpose, our usage of the electrical bike. This is why the specific battery is selected. So electric bikes, like other electric vehicles, frequently employ lithium-ion batteries because of their lightweight construction, high energy density, and comparatively low self-discharge rate. They are therefore effective and appropriate for supplying the required power for an electric bike. An aluminium alloy enclosure is used, which offers long-lasting and effective heat dissipation. An aluminium casing helps to reduce overheating and promotes greater overall battery performance and life. Generally speaking, the electric bikes run on voltage between 36 and 48 volts. The electric bike's motor and controller requires a certain amount of power within 48 volt battery can supply to ensure smooth and effective functioning. The 10.5 ampere hour rated capacity of the battery denotes the total amount of energy it can hold and discharge over the time. This capacity offers a decent compromise between weight and range, enabling the electric bike to travel a respective distance on a single charge. Motor power range, the battery's adaptability and capability to operate a variety of electric bikes model with different power needs are demonstrated by its compatibility with motor ranging from 250 watt to 1200 watt. Current and the battery's lifespan is extended and overcharging is prevented by the recommended charge voltage of 54.6 volt and 2 ampere charging current, which guarantees a secure and effective charging operation. The battery size and weight are manageable for an electric bike, so it may be readily included into the bike's frame or design without adversely affecting handling or balancing because of its high weight. To conclude, the lithium-ion battery that meets the given specifications is a good option for an electric bike because it can work with a variety of motor powers, has the right voltage, a good capacity, effectively dissipates heat, has safety features, and can withstand a range of temperatures.
Hello, my name is Asif Kamran and today I'm going to present the modeling and simulation as well as the results of a half-bridge LLC converter with battery charging and discharging. So here we have the entire Simulink model. On the very top you can see that this is the main circuit, which I will go into more detail in the next slide. And you can also see the PI controller, and you can also see the display monitors in which we can see the real values in real time of all the MOSFETs and diodes and everything. Right on your very right we have the switch which we can turn on and off to charge and discharge the battery, and the battery will discharge because of the discharging resistor. So going into a little more detail, you can see the diagram is labeled, right? So on your very left, we have the switching network, which consists of MOSFETs and diode, which are controlled by a PI controller at a frequency of 118.32 kHz. To its right, we have the resonant tank, which features a resonant capacitor, a resonant inductor, magnetizing inductor, and a transformer. Two IGBT switches regulate the current flowing through the resonant tank. To its right, we have the rectifier circuit, which transforms AC into pulsating DC, which charges the resonant capacitor and supplies the input for the half-bridge circuit. So finally, on your very right, we have the battery connection, which ensures that the battery can be charged and discharged, and we also have the current limiting resistor and discharging circuits as well, so that we can discharge the battery to see its outcome. So moving on to the result of the simulation, here we can see the MOSFET voltage and current graph. During the on state, the MOSFET current experienced a significant surge, indicating efficient current conduction and energy transmission to the resonant tank network. In contrast, during the off state, the current sharply drops to absolute zero, signifying the interruption of current flow. In this graph, we can see the behavior of diodes in the converter. The diode current graph illustrates the passage of current through the diode, peaking when it's conducting, enabling current flow to the output. Conversely, in the off state, the diode current reduces to a minimal level, almost like zero, due to its blocking nature. So this graph shows the behavior of resonant inductor current and magnetizing inductor currents, which are very important for energy storage and transfer. During the on state, the resonant inductor current steadily accumulates energy, subsequently releasing it to the resonant tank circuit during the off state. The current waveform exhibits a characteristic sinusoidal curve, which demonstrates their crucial roles in the conversion process. So here we can see the graph of output current and output voltage of the circuit. Across the switching cycles, the output current rises from 0 to its peak value of around 1.325 amperes during the on state. And simultaneously, the output voltage surges from 0 to 47.951 volts. During the off state, the output current gradually declines while the output voltage reduces as energy stored in the resonant tank circuit is transferred to the load. So finally, we have the battery charging and discharging graph. So here you can see that when we turn on the circuit, the state of the charge of the battery started rising from 5 all the way up to 5.0025 in just 0.6 seconds. And afterwards, I turned off the switch so that the battery started discharging because of the discharging resistor. So, and moving on to the battery voltage, we can see that the battery is maintaining a constant 48 volts, but when we turn off the switch, it's maintaining around 47.6 volts. And moving on to the battery current, we can see that the battery current is maintaining at 1.32 amperes, but when we turn off the switch, it becomes like around minus 0.3 amperes. So the battery is starting to discharge because same the discharging resistor. In conclusion, this study presents a comprehensive analysis of half-bridge LLC converter achieving efficient conversion from high voltage to low voltage and demonstrating battery charging capabilities. While it is successful in simulation, the real-world testing of the converter along with the battery integration and also with aspects like protection methods will determine the converter's success in real-world applications. Thank you very much for your time.